So it's time to start in this nice cool room. I will first add my best wishes to Giorgio for his anniversary and introduce Chiara that will talk about marginally stable equilibrium in critical ecosystems.
Thank you. I think I have a little problem with the mic, but it doesn't react. Can you hear me? No. It's just like turn it off.
Okay.
Now?
No, now it's mute.
And now?
Non è mio.
I'm changing. Now? Yes. Okay. Okay. So, okay. Thank you, Alain. And, first of all, I'm so very glad to be here giving a talk in what is my home university, and greatly honored to be part of this scientific celebration for Giorgio, and for his way of doing science, which often, but not only, steps through this glassy path on the way towards new discoveries. And I want to celebrate this way of doing science by telling you the story on how a glassy path was allowing us to say something new on ecosystems. And well, before starting with that, let me give you a little bit of a background in the area. And well, starting from the very general concept, maybe many of you know that in many subfields in biology, there has been somewhat of a revolution that arose when large data sets on the behavior of a system with a large number of interacting degrees of freedom have become available and have shown the emergence of new features at the level of the collective behavior. And among those features, there is one famous concept, which is the concept of self-organized criticality that has been observed in a lot of different contexts, and that arises with this feature of the development of long-range correlation across those systems. So I mentioned this, first of all, because we're going to see a similar phenomenon taking place in our example for ecological system, but also because a similar revolution seems to be happening in ecology nowadays, because similar to other subfields in biology, also in this case, very recently, latest technology have allowed us to assemble and track the dynamics of large co-cultures of bacteria, for example, or also to single out and study the different species in the gut of different animals or other colonies, or also colonies of bacteria in the soil, for example. And again, dealing with a large number of species that are interacting in these colonies, the approach that one can apply is the one of using a statistical mechanics study of some equivalent models that in this case are always, well, often disorder models. So in this situation, there has been a flourishing of recent works in which there has been some findings that go in the direction of showing how in certain situations there is the development of a glassy behavior that in this context must be interpreted in the sense of having a large number of equivalent equilibria that are characterizing our system. And I'm saying recent, well, a list of recent works, but as you can see from the dates of the publication, so the publication here, we immediately notice that there is an outlier in this list, well, which is not completely uncommon in the biological data, but in this case the outlier is interesting for us because we're talking about a paper of Giorgio and a student of his who, well, I wanted to show the abstract of this paper just to briefly mention how, in this, well, little flashback, how, well, more than 20 years ago, Giorgio was already asking himself many of the questions that this ultra-modern revolution in ecology is posing nowadays. And he was giving this answer about the possibility for the existence of a glassy phase. So replica symmetry is broken, was appearing in this abstract for this example of an ecosystem. And this is the result, coming back to the present, that I'm going to show you today. So the model that we studied in this case, we found this solution, spin glass solution for spin glass phase for the ecosystem. And on top of this, what we did is to connect this result with the emergence of long-range correlation in these systems, and also connect this result with what is a long-standing open debate in modern ecology, which is the debate about the stability of large ecosystems. So let me start by this last concept, by detailing what is maybe the most famous work that was boosting the debate about the stability of ecosystem. And this work, the work I'm referring to, is the work of Robert May of 1972. And this is a bright work. So Robert May was interested in large ecosystem and in the study of the stability for them. And when I'm talking of a large ecosystem, I'm talking of an ecosystem with a large number of species, as is the number of species. And when we want to describe the behavior of such ecosystem, what we have to do is to solve a system of typically ordinary differential equations that of this S ordinary differential equation that are coupled with each other, and that is in general very difficult to solve, of course. And the approach that May was proposing is the one of assuming that the system was reaching a stationary state, so a fixed point, and then he was proposing a Taylor expansion of the equation around this fixed point. So as you immediately see, this allows to translate these problems in terms of the problem of a system of linear ordinary differential equations in which, well, the constant coefficients are contained in this matrix A, and the new variable represents the deviation from the fixed point. And it's, of course, well known that this system will have a zero solution when all the eigenvalues of the matrix A are negative. And therefore, well, at this point, the problem is translated into this problem of finding these eigenvalues. But May didn't know how to deal with this matrix, and he was then introducing additional assumptions for this problem, like, for example, an assumption of strong stability for the single species in isolation, which is given by this -1 on the diagonal of the matrix of this, and then just random Gaussian entries for the off-diagonal entries, elements. In this way, he was, in fact, describing this matrix as a shifted random matrix and translating this problem of checking the stability into the problem of, well, a classical problem in random matrix theory, which is the one of finding the distribution of eigenvalue, and in particular, in this case, find what is the support of this distribution on the real axis. Now, at that time, of course, it was already known that a matrix of, well, the B-type, the one that was appearing here, that belonged to the Ginebra ensemble, is characterized by a distribution of eigenvalue on the complex plane, which is the celebrated circle law, which has a radius that depends on the variance of the Gaussian off-diagonal entries times the square root of the number of species. And for the shifted matrix, we will be talking about a distribution of eigenvalues, which is this shifted circle law that is centered in -1. So the shifted circle law will have a finite probability of having eigenvalues with real part larger than 0, only if this alpha square root of S is larger than 1. So in other words, May was giving this prediction that there should be a sharp crossover in the behavior of this, in the stability of this fixed point for the ecosystem between a less heterogeneous but unstable ecosystem and a more heterogeneous but unstable ecosystem. And well, as simple as it is, this paper had a tremendous influence in the following literature, boosting this debate, because it was contradicting, well, the experimental observation that we can see a lot of very large and very heterogeneous ecosystems that are existent, well, in nature. And within this debate, there was also, this work was also, of course, very much criticized because of the additional assumption that May was introducing for obtaining this result, and also because of the full inconsistency of this analysis when the heterogeneous, large heterogeneous ecosystem were taken into account, because the initial expansion didn't make sense and was not able to tell anything about the behavior of the system when we are describing this case, because this fixed point is in fact unstable. So what we did is to approach this very same problem by using a glassy path. And in this way, we were able to reobtain the result of Robert May in a fully consistent picture that also connected this result with this emergence of a critical behavior for the ecosystem itself. So to start this approach, let me introduce the model that we focused on, which is called the Lotka-Volterra model by generalization of the predator-prey, the classical predator-prey example. In this case, we are dealing, of course, with the variable n that represent the number of individuals in a single species, which in the ecological literature are called abundances. And we have, first of all, in the equation, a self-regulation terms that says that every species in isolation would stabilize at a certain carrying capacity, Ki, which means that species with an abundance is larger than its own Ki will experience overcrowding in the environment, and then this population will shrink back to the value Ki. Okay, so this is this self-regulation term. Now, following an hypothesis of homogeneity of the system and null information of what we know about the interaction between species, we just introduced these random couplings between, random interaction between different species. And we can also introduce elements like random fluctuation around the deterministic solution of the first two terms, and also an element that is an infinitesimal immigration rate. All this detail just to convince you that this is a model that is well accepted in ecology. And well, even more than that, there is this recent paper that shows that by changing the different parameters of this model is able to describe the behavior of other models that were thought to be structurally different with each other when a higher level of irrelevant details were taken into account. So it is a model that may have quite interesting behavior from the ecological point of view. Now, on top of this, what we did is to add a further assumption, which is an assumption of symmetry of the interspecies interaction. And this was useful for us because in this way we could rewrite the equation in terms of this an Hamiltonian that is controlling the behavior of the system, and stepping through a Fokker-Prahn formalism, we were translating the problem of finding the stationary point for this system of equation into the problem of finding the minima of this corresponding Hamiltonian. And as you can see from the structure of the Hamiltonian that we obtained, we have well, it shares a lot of similarity with an Hamiltonian of spin glasses, but it also has some peculiarity, which is this single species potential that says two things. The first is that single species in isolation again equilibrate and stabilize at the carrying capacity Ki, and also that these variables in which this problem is expressed are the abundances, which are always non-negative. By solving this, well, not solving, by looking at numerical simulation of this model, it was possible to obtain this phase diagram for the behavior of this system. That is expressed here in terms of the average of the interaction and the variance of the interaction, which is in the ecological literature also called the variability of the ecosystem. And the result that was obtained through numerical simulation was consistent with the existence of a single minimum, which is stable under perturbation when a small variability is considered. While if you go to too large variability, we end up with an unphysical situation in which there are some species that are diverging. And this simply occurs because sometimes particularly advantageous interaction between the species can compensate this overcrowding term that was keeping the abundances finite. And we are not going to be interested in this regime. But for positive value of the average of the interaction, at an intermediate variability, there is a third phase that appears. First, let me tell you that this regime is a particularly sensible one, because it's telling you that the system is typically in a competitive environment, and that there are some rare mutualistic interaction that takes place in this situation. And then from the numerical point of view, in this regime, what it was observed is a solution that is consistent with this presence of a large number of alternative solutions, because it was observed that starting from different initial conditions, the final composition of the ecosystem was found to be always different, and also that this solution was changing when the system was perturbed a little bit. And again, this was telling us that this multiple equilibria solution should have a lot of many of the features in common with the spin glass phase, not to talk about the Hamiltonian that we were starting from. So of course we decided to study this model, and in particular this multiple equilibria phase, with the tools that have been developed for the study of the physics of spin glasses, and in particular with we studied this introducing replicas. Now, given the audience, I will not maybe venture a cartoonish explanation of replica. What I will just simply do is to stress an important fact, which is the fact that this method is, has its power and flexibility to show and describe a system with which there are a large number of minima, and it is able to describe this landscape even in the case in which these minima are nested in a hierarchical structure of larger and larger basins. And in this case, what this replica method is allowed to do is to describe this multi-minima structure in terms of the width of a single minimum, but also the distance between two different minima, or the overlap between two different minima, and the distance between two different minima that belongs to the two different basins. And I'm telling this because one quantity of particular interest for us will be the fluctuation within a single minimum that will be connected with the fluctuation of single species abundances during the dynamics in the long time limit. And it is a quantity that, first of all, we can measure in simulation, and then in the long run might be even evaluated from the experimental data, so it's important for us. So by using the replica approach, we started to obtain result at the level of this quantity, which is this fluctuation within a single minimum, and we could compare it with the outcome from simulation. And here I'm talking about the result that appears for small variability. This result is compatible with the solution that characterizes the physical situation in which we have a single minimum. So it corresponds to the replica symmetric solution, the replica symmetric ansatz. And from what we can see, well, the prediction from the approach, the analytic approach, can easily, very well track the numerical result. But at a certain point, a finite value of the variability of the interspecies interaction, what we have is that this replica symmetric solution would continue to grow while the numerical result flatten out, okay? And so we see that this solution will not be able to follow, to give a good account of the numerical prediction. And also what we checked is that this replica symmetric solution is losing its stability at this point. In particular, yeah, sorry, these are just to show that there are sample-to-sample fluctuations that becomes important in this phase, okay?
One log is a single sample?
Yes. So you should imagine there is a spreading of the result around this value. We added more plots in the figure on the paper, just. What we did is to, again, I was saying, studying the stability of the replica symmetric solution. And of course, we did this by looking at the eigenvalues of the Hessian of the replicated action. And we found that there is an eigenvalue, the replicon, that is becoming negative right at the point at which we see the replica symmetric solution is not able to give prediction for the numerical result. Well, as Giorgio would have immediately said at this point, is that we should go to further the next replica ansatz. So we went to the one-step replica symmetry breaking, and we found that the situation was improving. So the replicon was less negative than what it was before, but it became negative at the very same point. Which means, of course, that what we should do is to go to the full RSP solution. And this is indeed what we took into account. And what we did is to use all the feature of the full replica symmetry breaking solution, which is the spin glass phase, to obtain predictions for the ecological model. Now, of course, the first feature is that it arises when there is a large number of alternative equilibria, which matches with the expectation from the numerical simulation. But a very important feature that many of us here know is that this spin glass phase is a critical phase, which means that the replicon eigenvalue remains equal to 0 across the entire range in which the spin glass phase exists. And well, this has a lot of consequences because in this particular case, the vanishing of the replicon, which stays there across the entire phase, sets a number of conditions on some interesting observable from the point of view of the ecology. And one of them is this fluctuation of single species abundances. So just imposing the vanishing of the replicon, we were able to obtain the result, that is this red dashed line here, that was able to give account for the numerical result. Again, there are just some sample-to-sample fluctuation that deviates from it. And also, well, we could obtain prediction across the entire range of the variability for the interspecies interaction on another variable that is of particular relevance in the ecological literature, which is this phi, the diversity. The diversity of an ecosystem is the fraction of surviving species out of the pool of S possible species that are at disposal. And this quantity has an interesting behavior. You see that even in the range for small variability, this quantity departs from 1, so it goes smaller than 1, which simply means that the weakest species will never participate to the final unique composition in this regime. But beyond this critical value of the variability, again, we have to use the full replica symmetry breaking solution, and in particular the condition that comes from the vanishing of the replicon eigenvalue to describe better the numerical data apart from some finite size scaling in this case. And well, I want to spend a minute on this outcome because this contains the message of, well, the main message of this work. What is this result telling us? It's telling us that in this case, species are self-consistently selected as to pose the system at criticality, because there is a straightforward connection between this criticality condition and the fraction of surviving species, which means that dynamically the system will evolve by killing a certain number of species until it will reach a final configuration, a final composition in which there will be long-range correlation. And this is a nice example of self-organized criticality for this kind of, in this kind of setting. Now, beyond this, I want to make another comment. On this result, if you look at this relation, that is the relation that we were obtaining for this diversity, while imposing the vanishing of the replicon, we found a striking resemblance of this condition with the saturation of May's bound for the stability of large ecosystem, and in particular for its version for symmetric ecosystem with symmetric interaction, and where the random interaction coupling are rescaled as we did. So this would be the correspondent condition from May's analysis, and this is what we obtained from the vanishing of the replicon. But the thing is that the two were obtaining using two different approaches. So we weren't fully sure of their straightforward connection until we looked at the stability of the system under small changes of single species abundances. So in this case, what we did is to introduce suitable fields that couple to single species abundances, and we studied the response of the species abundances under small variation of these fields. And we obtained something that is connected with the stability metrics that May was studying in the first place. Apart from the fact that in this case, this stability metrics we don't have to introduce assumption on its structure. What we just do is to evaluate it at the fixed point, that is the final configuration, the long time limit for the ecosystem. And in the simplest case that we were studying, the stability matrix was found to have a very similar structure to the one that May was in fact proposing. There is a diagonal term, and then there are random off-diagonal entries. But we should be careful here, because these off-diagonal entries at this point develop non-trivial correlation. And why so is because at the beginning these were the just random interaction between species, but the interaction that appear here are the interaction between the species that have survived. And those have survived because of those interactions. Okay, so we shouldn't be sloppy here and do not consider, at least at the first approximation, the fact that this should develop correlation. And well, we would have been stuck here had it not be for the richness of the spin-glass literature. And so what we did is to pick up this nice computation of Bray and Moore, which allowed us to show that the eigenvalue distribution for a matrix of this type in the large S limit converges to this, the eigenvalue distribution of another matrix that have random entries that are uncorrelated this time. Okay, so this is something that you can actually evaluate. So, well, in this case, this corresponding matrix with the same variance for the off-diagonal entries was the Wigner semicircle law, which has this support, in this case, expressed in terms of the diversity of the ecosystem. And if you remember, well, the condition that came from the criticality, this corresponds to this, the fact that this support is touching 0 in the entire glass phase. This is a situation that goes under the name of marginal stability, and as you can see, this corresponds to the saturation of May's bound that will take place across the entire spin glass phase. So just to recap, what we observed is a situation that as a function of a solution that as a function of the variability moves from a single minimum that is stable under perturbation to a multiple minima glassy phase that is critical and that is marginally stable, whose all the minima are marginally stable. And well, such that, in fact, the diversity will pose the system at criticality and at the edge of marginal stability. All these are the feature that comes from this interesting phase. Now, these are the results from the numerical simulation, and as you can see, well, they agree very well with what we were predicting, but what we can also do is to study variation of this problem, and even in the case in which the distribution of eigenvalue doesn't follow the Wigner's semicircle law, we are ending up with a spin-glass phase that obeys to this feature of criticality and marginal stability. So in this context, we were able to generalize maze bound for stability to other situation and having a formula that is valid for different possible ecosystem that we could think of. And so this is all about the analytic prediction, but I want to spend a few more words on how to reveal the evidence for this full replica symmetry breaking solution, the spin-glass solution from maybe experimental data. Of course, the first evidence, which is the intuition we had since the beginning, is that this would introduce an history dependence, so a dependence of the final configuration from the initial condition. But this feature of marginal stability would also be at the origin of slow dynamics and aging phenomena, as long as this minima, these stationary points of the Hamiltonian with flatter and flatter direction are approached. And then the criticality feature instead of this phase would give the most striking evidence that this phase is actually present and characterizing the behavior of the system. So, well, we should expect the divergence of susceptibility or responses to perturbation, but the problem is that it's already well known in the spin-glass literature that this is not the case for usual susceptibility. That maybe is what in ecology people might have tried. So from the know-how of the spin-glass community, what we were proposing is to look at the spin-glass susceptibility to observe the critical behavior of this phase. And again, let's say the time-dependent counterpart, which goes under the name of the chi-4. And again, in these two cases, this is a quantity that is accessible to the, using the data from experiment, because it's enough to know the abundances of the single species, which is something that starts to be at disposal to evaluate this quantity. And so to finish, I want to discuss and speculate on what might be the different situation that arise when we consider slight variation starting from the initial model that we considered. For example, we could consider to add a small demographic noise on this solution. We were until now working at zero demographic noise. And well, in this case, we would expect that for finite ecosystem, the whole global picture would not change at the qualitative level, but this small demographic noise could allow the system to jump from one equilibrium to the other, giving somewhat of an intermittent dynamics across different composition. That is something that has started to be observed in this numerical work here in 2015. And similar phenomena of avalanches of extinction and recolonization, as it is called, this phenomenon in the ecological literature, could arise when applying small perturbation to the equilibria that the system has reached. Now there is this comment about the symmetry of the interaction between the species. We could think what happened to the dynamics when we are considering instead a small asymmetry in the game, And in this case, we could expect the arising of a new qualitative feature in the dynamics that would, for example, be represented by a circuitation of these dynamics across the vestige of these minima that did characterize the original Hamiltonian. And otherwise, we should think and set up a whole new approach to study the fully asymmetric regime. And this is something we started to work on. And if you want more details about this, we have in the audience Felix Roy, who is writing in these days the first paper on this topic. And there is nice evidence of maybe the emergence of a chaotic behavior. So a lot of interesting outcome come from this analysis. And well, more in general, there is, we are working also on the study of different immigration protocol, and also to the in the interesting case of multiple species interaction. In all these situations, we pay a lot of attention to this definition of observable that might allow to really connect this picture with the experiment. And I guess I should stop here, but not before concluding this path with stressing again that even in the case of ecological system with a large number of interacting species, the full replica symmetry breaking and this spin glass solution were the cornerstone for giving a prediction, at least in a certain regime of the parameter, which is the high variability of the interaction between species. And here I'm reminding you the prediction that we gave in terms of the diversity of the ecosystem. And not only it was useful for giving prediction on the actual value that we should observe, but also a prediction starting from the feature of a criticality of this phase, a prediction on what we should observe to see whether this picture is actually characterizing the behavior of the system. So we were proposing this new observable to be looked at from the experimental data, and also exploiting the feature of marginal stability that characterized the spin glass phase. We were setting the May result, this May condition for the stability of ecosystem, into a fully consistent picture that doesn't really suffer of the limitation that the original picture had. And I stopped with this, but before really stopping, I really want to thank Giorgio for tracing this path for the first time, well, and all the works that followed in this very rich field. Thank you, Giorgio, and happy birthday, and thank you all for your attention.
Okay, thank you, Chiara.
Thank you.
So we have time for a couple of questions.
Do you think the ecology community will be interested in using our methods and our developments? I mean, we know that different community reacts in very different way, right?
Yeah, it's true. So in our case, we were lucky because we were working with this with Guy Booning, who spent a lot of time in really going deep down in the what are really the question that in the ecological community should be answered and everything. So they are interested. Of course, every time you introduce an assumption, there must you meet some criticism in that. That's why it's so important to extend the analysis to more realistic situation by studying different immigration protocols and everything. But we really started to discuss with people that, let's say at the beginning, with people that are at the boundary between the two fields. And I think, yes, there is the possibility to go in that direction.
Hi.
So my question is entails with the last slide where you say the perspectives and especially so my impression, I'm not an expert in ecological networks, is that ecological networks are really strongly asymmetric in the sense that I feed on your species, you typically don't feed on my species, and so they're.
Yes.
So they interact. So
yes, there is the whole. Yes, this is what I was also answering to. And so there is this big issue of the symmetry. So maybe one specific example in the reality might go in the direction of small asymmetry, but in general, the typical situation is that we deal with strong asymmetry, and this. So the study as a function of the anti-correlation parameter, the parameter that controls the anti-correlation between coupling of different species is the study that one has to do. And this is what we started to do from the case of uncorrelated couplings, so fully asymmetric situation. And again, in this case, there are much richer dynamics that arise. But I think that we could keep in mind what is this, what is the feature of the system in this specific case, because this aging might arise together with the chaotic behavior, and if we didn't know that there was this additional ingredient in the game, we could have missed some of the feature. So it's true that it's going to be more complicated, but we are starting with a piece and then.
Okay, thank you very much.
Yes. Look, I've been interested some years ago in these questions of the May, and I talked with ecologists, and they were not so convinced that this result was wrong. In fact, they were telling me that you have to introduce another concept, which was the resilience of an ecosystem, that the stability of an ecosystem was very difficult. You mentioned that it was clearly wrong experimentally. They were not telling me that.
No. I say that it started this debate since observation were not fully in agreement, and I know that within this debate there has been a lot, starting from May's paper, okay. There was also a way out from the apparent contradiction that was considering the fact that actually the ecosystem was structured in blocks of more connecting species, and then the blocks of more connected species will be less connected with each other. So it was like splitting the problem into small ecosystems that are like less connected. And then he was finding himself a way out. So there are many different approaches that deal with that and try to go beyond the apparent contradiction. But it's true that, yeah, it's not.
So the question is, have you speculated about where could one do a field study of an ecosystem to see what is the behavior of a real ecosystem or something like that, an island or whatever? Where could it be that you can study a real ecosystem, I mean experimentally? I mean the speculation.
So it depends. No, I understand.
It's not your job. It's the job of the ecologist.
It depends on the ecosystem we want to describe. Okay. So if we are talking about an ecosystem that involves species like macroscopic species, like big animals and plants and everything, it's way more complicated. We should start to introduce a strong assumption on the big structure that characterize this ecosystem. But the aim of this approach, and that's why I'm telling it's something that has to do with modern ecology, ultra-modern ecology, is that it wants to describe this ecosystem in which everything is very homogeneous, in the sense that all the different species interact with rules that are homogeneous with each other. So we are talking about bacteria, for example, which all share this competition in the, like, taking advantage of the food in the environment, but also sometimes mutualism. There is a lot of new experiments that try to, like, understand which are the small elements, the microscopic behavior, so to develop a consistent picture at the large scale, okay? Then otherwise you should go and look at the macrostructure, and I was mentioning this paper before that shows that this Lotka-Volterra model, as simple as it is, can cover all these different features, that shows that even for the macroscopic, if you are able to track which are the big macrostructure in the game, and you use the Lotka-Volterra model to characterize this different macrostructure, you can obtain the same result if the number of species is large enough. So that's the interesting of that.
Hi, I have a question regarding when you introduce asymmetric couplings, not only the
yeah, okay, sorry, I didn't see.
not only the instability is important, but also the transient instability, which is controlled by the pseudo-spectrum and not the spectrum of the operator. I was wondering if in this framework you can actually tackle or study the pseudo-spectrum rather than the spectrum.
Well, if you're talking about asymmetric coupling, this framework would not, I mean, the approach we were using that goes through the analysis of the Hamiltonian will not be able to describe this, the result.
So how do you, sorry,
so
then what
we should use rather this, a more dynamical approach. Okay, that's. Thank you.